Okay, let's talk about a couple in the woodwork here. So this one here, now notice it says A represents the measure of an angle in radians swept counterclockwise from 3 o'clock. Okay, but notice that then we have an argument 0.7A. What does the argument 0.7A represent? If it's going into cosine. It has to be angle measure, right? Anything, whatever goes into cosine, we know the input of cosine has to be angle measure. So, but A is the measure of an angle. So in this problem, there are two different angles going on at the same time, right? So A is some measure of some angle, and 0.7A also has to be a measure of some angle. So what we have is two angles, the measure of two different angles. So there are two different angles in play, okay? The angle A and 0.7A must be an angle as well. 0.7A must be an angle measure as well. So what's the argument of the function g? Right. The argument is always the whole thing that's going into cosine or going into sine or whatever function you have. Okay, so our argument is that 0.7A. What type of quantity is the argument? So what type of quantity is this 0.7A? Angle measure. It's got to be angle measure. If it's the input, if that argument is what's going into cosine, it has to be angle measure. All right. What interval of the argument will result in a full cycle of the function g? Yeah, this is how we find period, right? So we say that argument, when the input of cosine hits 2 pi, we get a full cycle. So that input of cosine now is that argument, 0.7a. So from 0 to 2 pi is what the argument has to do. So now write an equation setting the value of the argument equal to the angle measure resulting in one full cycle g. All right? Setting the value of the argument, 0.7a, equal to what angle measure results in a full cycle? 2 pi. So that's what we're doing there. What's that?
What are the units? Is it pi the unit, or does that include units or grams on the one above it?
Oh, sorry, units. So what are the units of the argument of cosine? What are the units of radians? Radians. And so that's RAD. Okay, so then use your answer in part D to find the interval length of input that results in a full cycle. So what is our input? A was our input. So what input value of A makes the argument equal to 2 pi? You're going to solve for A, right? So yeah, 2 pi divided by 0.7. Okay? And what's the period of G? It's what we just found, right? What is the period? The period is exactly this. It's the interval of input that will result in a full cycle of output. They're describing the period right here. That statement right there is exactly the period of G by definition. By definition, that's the period of G. So it's the same thing. That's what you just found. Okay, questions on this problem that caused a little bit, it had the lower success. Just see the green. Uh-oh, I forgot units. Again, so now the period of G, what period is input value, so we got to make sure that, so we've seen that input could be time, or now we're seeing that if it's input, it says A represents the measure of an angle in radians. So if A is our input and A is also angle in radians, then the period will have a unit of radians too. But we saw that the input of these cosine and sine functions could be time. So In a different situation, here we might be putting seconds or minutes or hours. Okay, whatever the unit of the input quantity is. There we go. Now we got it. I think number 2 is just like it, so we'll just go on. Yeah. So number 2 is a similar, but is it time this time? So now they're doing time, right? So now the input is time, and what will 30t represent? What quantity is 30t, the argument? Angle measure. What goes into sine as a whole, into cosine, is always angle measure. It's always angle measure. That's why we're working on these definitions so much the last 2 weeks. The input into sine is the measure of the angle swept counterclockwise from 3 o'clock. Same with cosine. So, but now the input into h is time. So we got both going on at once. Time is the input into h, but 30 times time will be the angle measure going into sine. All right, so that's everything else is the same though for this one. Okay, so let's open up to page modules 7, investigation 7. Tell me what page that's in. Way toward the back. 291? 291, page 291. So start with question 2. Okay, so it says that a bike on a rack, such that the tech can turn the pedal with his hands, causing the back wheel to rotate as well. So I got this shown up here. On this bike, the circular path swept out by the pedal is the same size. Circular path is exactly the same size as the circular path swept out by the tire. I don't know what that means. Suppose that when the pedal starts at 3 o'clock position, the tire valve is pi/4 radians clockwise from 3 o'clock in quadrant 4. So here's the starting, before we start turning it, this is the situation up on the screen. Okay, let theta equal the angle measure of the pedal counterclockwise from the 3 o'clock position. So theta is our angle measure turned by the pedal, the one on the left. Okay, and so you're going to fill out this table to get these corresponding angles. So when theta is 0, pi/6, pi/2. So no calculator, so you can write expressions. Write expressions for the corresponding angle of the tire valve. So here we're going to start turning it, and notice what? The tire valve, what's the relation of the tire valve's angle measure to the pedal's angle measure? Both measured from the 3 o'clock position. Okay, good. Did you hear that? It's always pi/4 behind. It's always pi/4 behind. Okay? So if that's the case, then fill out that table. Don't use a calculator. If you need to write expressions, write expressions. So given those angles of the pedal, write the angle measure of the tire valve. And if you flip to the next page, the point of that table is then to answer B, part B. So for any theta that's swept out by the pedal, how would you describe the angle measure of the tire valve in terms of theta? So we want to write the angle measure of the tire valve in terms of theta. Equals what? It's up here. What do you think? For instance, given that theta has swept pi over 2, what's the angle measure of the tire valve right now? Pi over 4. Given that the pedal has swept 3 pi over 4, what's the angle measure of the valve? Pi over 2. Okay, given that the pedal has swept 3 pi over 2. Get that. Right. There. What angle measure do we have for the valve? Should know what that from our unit circle, right? So remember, count. 1, 2, they're pi over 4s, right? 1, 2, 3, 4, 5 pi over 4. So given any angle theta swept out by the pedal, what's the angle measure of the tire valve in relation to theta? So what's been said is theta minus pi over 4. Agree with that? Yeah, it's always, and someone back here said, it's always lagging behind. The angle of the valve is always lagging behind by pi over 4. Did you buy that? It always lags behind by pi over 4, so then it makes sense that it's going to be the angle of the pedal minus pi over 4, because it's behind. That should make perfect sense. Does it? Okay, so if we wanted to write, so now they have a couple functions p and t there. P is the vertical distance above the horizontal diameter of the pedal. Is it in fraction of a radius? Isn't it radius length? Is that what it says? Yes? Yeah. So we want the vertical distance of the pedal above its horizontal diameter in its rotation there as a fraction of the radius. So you're going to write that function. What function is that? We should know that by now. That's the sine, right? That's just exactly what sine gives. It's sine of theta. That's going to give the vertical distance above the horizontal diameter. For any angle theta, right? So theta is changing. Theta is the angle swept out counterclockwise from 3 o'clock. To track its vertical position as a fraction of the radius length, sine theta does that, right? It takes on all the values between what and what. Sine theta takes on all values between what lowest value and what highest value. Sine theta, vertical distance. The lowest value it attains is -1 at 3 pi over 2, or whenever it's at the bottom of the circle. And the highest value sine attains is 1 radius length up, right? Okay, now we want to write a similar function over here for the tire valve. We want its vertical position above the horizontal diameter in radius lengths, but we want to write it in terms of the pedal angle measure. So it's going to be sine. Here's the deal. If we want the function t to output the vertical position of the tire valve, then what angle needs to go into sine? The angle of the pedal or the angle of the tire valve? if we want the function t to output the vertical position of the valve, then what needs to go into sine? The valve angle or the pedal angle? Valve angle. If it's giving us an output about the valve, then the input has to be about the valve, right? Or the argument. So this has to be the valve angle measure. Right? You put the valve angle measure in, you're going to get the valve vertical position. Makes sense, right? You put the valve angle measure into sine, sine's going to give you that vertical position of the valve. All right? Well, what is the valve angle measure? Right, and so but now the input of the function is the pedal angle, right? So the input of the function is the pedal angle. But if we want the valve vertical position, we need an expression for the valve angle measure, but that's what we found up here, right? That's what we found right here. So the valve angle measure, which is always pi/4 behind the pedal angle measure. If we put valve angle measure into sine, we're going to get vertical position of the valve angle, valve measure, the vertical position of the valve out of sine. But it's just doing it as a function of the pedal angle measure. Does it make sense? This is important. So we've got input and argument, right? So input and argument. So let's practice. So explain what in the function t, what's the input? What does it mean? And what's the argument? Tell the person next to you. In the function t, what's the input quantity and what does it mean? What's the argument quantity and what does it mean? Go, tell the person next to you. Okay, so what is the input into the function t? What's the input? He wants the angle measure of the pedal. Is that the input into t? It's theta, right? Theta is the input into t. We see that right here. It's our quantity. That's our input into t, and we know theta is the angle measure swept by the pedal. What's the argument of the function t? Or in this case, the argument of sine. It's the argument of sine. Theta minus pi/4. It's the entire thing that's going into sine. And what angle measure is that? That's the angle measure of the valve, so that the vertical position we get from sine is the vertical position of the valve, right? If we put whatever angle we put into sine, whatever measure, that's what we're going to be tracing the vertical position of. Okay? So let's talk about now creating these graphs. Okay, so P of theta equals sine theta. So that's what? That's just tracking the vertical position of the pedal as a function of its own angle, right? Of its own angle measure. We should all know what sine looks like. Can you sketch sine, which is basically tracking the vertical position of the pedal? So we do that here. Okay, what's it going to look like? So what's that graph going to look like? Does it start at the min, the midline, or the max? At the 3 o'clock position, vertical position is -1, 0, or 1? 0, and in the first quadrant, it does what? Increases to 1. So as we go from 0 to pi over 2, the height of that pedal is going to go from 0 to 1. Okay, second quadrant, as the pedal angle changes from pi over 2 to pi, the sign changes from 1 to 0. We're tracking vertical height, right? Vertical height. So it's back to the midline now. And then down to -1 at 3 pi over 2. And then back to the midline, 0. So that's our function p. Our function p. And then we could, another rotation, we'll just show the same cycle of output values, right? Okay, so I want to put that same graph, I'm going to put that same graph over on the right. So it's still this is still the function p. I think. No, what am I doing wrong here? Let's try this one. There we go. So they're both showing p. This is not the valve. This is the pedal, okay? Just, I'm replicating that pedal graph over here, the blue one, on the right. And so what we want to do now is we want to talk about the function t, which is tracking the vertical position of the tire valve. And how is the tire valve relative to the pedal? Is it ahead or behind? It's behind by pi over 4, right? It's lagging behind. So we're sweeping an angle with the pedal, and then the tire valve is always behind by pi over 4. So when the pedal is at pi over 4, what is the angle of the tire valve right now? 0, right? So because it's behind, right? So now it's starting its cycle. So when the angle of the pedal hits pi over 4, now the tire valve is going to start its cycle, its normal cycle, right? So that's what? That's here. And starting there, we're going to imagine that the tire valve is going to start its cycle because it's lagging behind, right? It's lagging behind by pi over 4. So what is the graph of t going to look like? If it's lagging behind by pi over 4, where will that graph be relative to the graph of p? What would behind mean? Would it mean shifted to the left or shifted to the right? It's behind. It's behind. It doesn't start its cycle. Look, it doesn't start its cycle until theta hits pi over 4. And now it's going to start its cycle. Shifted left or shifted right? Let's see it. So once the pedal angle hits pi over 4, now the tire valve starts its cycle. It's behind, right? It comes later. The cycles of the tire valve are coming later by pi over 4, thinking of theta increasing from left to right. So you have to see this as, here's theta going by. So pedal comes first, right? Pedal starts its cycle, then pi over 4 later, valve starts its cycle, and is always lagging behind for increasing theta to the right. So you have to see that. So let's see it, ready? So pedal starts its cycle, and then tire valve starts its cycle, and it's lagging behind for increasing theta. So you have to see that red graph as coming pi over 4 behind the blue graph. Do you see it? Thinking about theta increasing, pedal pedal angle has a head start. It starts first, and then for a greater theta, then the tire valve starts its cycle. Okay, so when an angle lags behind another angle, that actually moves its graph which way? To the right, because it starts later. It cycles and it transpires later by whatever amount that, in this case, pi over 4. It's transpiring pi over 4 later. Do you see that? So we're trying to see why subtracting from the input moves the graph right. Why does it move to the right? Because moving to the right means that cycle is starting and transpiring later than the original theta cycle. So yeah, that's what we're trying to see there. That it should make sense. It shouldn't be counterintuitive that when you subtract you move right, but it should make sense that when you subtract the graph would move right. It's all about because that angle cycle is later, coming after. Okay, so now what about if so let's do a similar example, but now let's do so what do you see about the tire valve now? What do you see about the tire valve now? It's ahead by how much? Right, so now it's ahead by, I would have to tell you that. You wouldn't know that for sure unless I told you. But I am indeed telling you that now the tire valve is ahead of the pedal by pi over 6. It's ahead of by pi over 6. And let's do, so does the book track for this one? Pi over 6 clockwise, right. Okay, so this is number 3 now. And now we're going to track the horizontal distance. So mathematically, how would you describe the tire valve angle in terms of the pedal angle? So what is the angle measure of the valve in terms of the angle measure of the pedal? Right, theta plus. And does that make sense if the tire valve is ahead by pi over 6? You add, right? If it's ahead by pi over 6. You're going to add pi over 6. Should make sense. So now we're going to track horizontal position. Horizontal position of the pedal. What function would that be? Horizontal position of the pedal. Let's call it F and G now. So different. So we'll call this one F. And this one G. So F theta is the horizontal position of the pedal to the left of the vertical diameter. What would it be? Cosine of theta. And now we want to also track the horizontal position of the tire valve. So it's also going to be cosine. And if it's the horizontal position of the tire valve, then cosine of what? Whatever angle measure for the tire valve, right? So if we want the horizontal position of the tire valve, we're going to input into cosine the horizontal or the angle measure of the tire valve. Okay, and what does cosine look like? You should know that. This is sine. I want this one. There we go. Horizontal position, what, starts at 1. At the 3 o'clock position, or horizontal position is max. And then as you go to pi, it goes to the min, right, to the far left side. So that's what that graph shows. And we'll just go ahead and put that on both graphs. This is our f function, measuring horizontal position of the pedal, So if the valve angle is ahead by pi over 6, then what about the cycle of the valve? What about the cycle of the valve when the pedal angle is 0? It already started, right? So we already have seen. So if we're starting the pedal cycle when its angle measure is 0, then the valve has already started its cycle by how much? Pi over 6. So if I turn on, notice it's already started. Can you see that right there? So, but when the pedal angle starts, if the tire valve is ahead by pi over 6, it's already started its cycle here. And so if that angle measure of the argument is ahead of the input angle, does that shift the graph to the left or to the right? It's going to shift it to the left. Being ahead means it comes first. If it's ahead, it comes first. Its cycle is starting and transpiring ahead of or before the actual input angle. So this is going to shift the graph pi over 6 left, so that it's ahead. That angle measure is ahead, and it's doing its cycles before the pedal by pi over 6. Okay, any question on that? So the key is that there's 2 angles at work. There's 2 angles at work. There's the input angle, and then there's the argument angle. And if the argument angle is greater than the input angle, if it's bigger, then its cycles are coming before, and so that shifts the graph left. If the argument angle is less than the input angle, so we've got something minus, then those angles are lagging behind, and they're going to come after, and after is to the right. So again, the fact that it's plus and shifted left now should make sense. It shouldn't be like, oh, you always do the opposite of what you think. No, this is what you think. If the angle measure is ahead by that much, then it's starting earlier, and that makes sense. It should be left. Okay. Any questions on that? All right. So while you are while I'm getting something ready here, go back to number 1, page 289. And work on number 1 for just a couple of minutes while I get something ready here. Is this? Okay, I think this is the one that you have in your book. Is that right?
Yeah.
Okay, so this we're gonna start doing now. We're giving these curves. We're gonna write the functions for the curves, and then given real-world situations, we want to model real-world situations with curves like this for cyclic behavior, things that keep repeating over and over again, like circular motion. Okay, so we've got all these different things going on. We've got the period, we've got the midline, we've got the max and the min, the amplitude, and so we've got to put it all together now. Okay, so the first thing we always want to look for is the midline. The midline is a horizontal line. It's like that halfway point between the max and the min. So it's going to be y equals something. So for this example, y equals what? So if you need to, you can just find the max and the min and take the average. Take the average of the max and the min if you can't see where it is. So you should find that this one is at -2. Okay, and so then along with that, our max is, the highest point attained by the graph is 3, and our min is, can't see it here, but is it negative 7? So this then takes us to the amplitude. The amplitude then is from the midline up to the max or down to the min. So our amplitude is 5. It's always the positive version of that, right? So it will always be positive. Amplitude is from the midline up to the max, or the distance from the midline down to the min, but it's always a positive value, so 5. Okay, so then we have to look at the period, right? So look at the period. So the period is what? The interval of input that results in a full cycle of output. So what along our scale here, our input scale, this is the scale on the horizontal axis. What interval of input do we have that gives a full cycle of output? So we're looking along, so you have to look along the midline for that. So what interval of input does it? Right here, right? So our full cycle is we're starting here at the midline, back to the midline, and then down to the min, and then back to the midline. Period is about 4.2. Do you see that the period is about 4.2 on this? Okay, so then we have to decide, is it a sine graph or a cosine graph? Well, it starts at the midline and goes up to the max, and then back to the midline, down to the min, back to the midline. So this is exactly what sine does, right? At the 3 o'clock position, we're at the middle, right? And then we go up to the max, and then back to the middle, down to the min, and back to the middle again. This is exactly what sine is. So if we want to do this most easily, we're going to use sine. Okay? So sine of something. And then since the midline is at -2, we're moving the whole sine down 2. So it's going to be -2. There's our midline. And then normally, what's the amplitude of just sine by itself? So how far up does sine go and how far down does sine go? If it's measuring fraction of a radius length, then what's the normal amplitude of sine? 1. But this here, we got the amplitude of 5. So instead of going between 1 and -1, we're going between 5 and -5. So we're gonna put that 5 out front, right? We're multiplying all values between -1 by 5. We're stretching it by 5, right? So last is, we need a period of 4.2 to result in an argument here of what? This is what you had in your homework? So when x reaches 4.2, or the input reaches 4.2, that argument has to reach 2 pi. So we can just generally, we can say, call it like b times x. And the question is, what is this coefficient b that makes that whole thing be 2 pi when x hits 4.2, right? So when we hit the period of 4.2, we need a full cycle, so that whole argument has to hit 2 pi. So we're solving for b, so b times when x reaches 4.2, that whole thing has to be 2 pi. And that allows us to find what b is. Solve for b now. And it is 2 pi over 4.2. Okay, any questions on that? So if that's right, that's exactly what that is. 2 pi over 4.2 x sine -2. So all day Wednesday we'll be doing lots of these, but we'll get the horizontal shifts involved too.
Oh, hi, sir.